we will actually continue on with chapter 20 because I got a little less than halfway through it last class period. So going right in, I skipped over this picture. Oh, you got a question, Brandon?
Do you have any of the test questions?
Sure, they're right there. Okay, so I skipped over this for some reason. Maybe I was in a rush. But this here, you see the pretty ruby, and you see the pretty sapphire. And then you see this thing down here in the corner. This here is what I, as a physicist, call sapphire, or our textbook or gemstone people call corundum. So what's the difference between these three different, very similar looking things? Okay, color. What makes the color different? Impurities. It's impurities. The ruby has chromium impurities. I believe the sapphire has cobalt impurities, although it could also be iron. You can get blue from iron, you can get green from iron, you can get brown from iron. It depends on their oxidation states. And the corundum, that's pure. So if you want the pure sapphire, then it looks like this. This is what naturally occurring, uncut, unpolished sapphires look like. So you can see different colors here of the sapphires. How do they make something that looks like these into something that looks like, well, let's go with something of similar color, that ruby. They cleave it because they have certain planes where you have weaker bonds and a nice arrangement of atoms. If you put your blade parallel to that and tap it, it easily breaks. And so that's how they get these facets. And of course, oftentimes then they polish as well. But I just wanted to make sure I covered that and go to a question that we ended, or we didn't end with, but we had near the end of last class period. Physical properties of a mineral are predominantly related to, just to make sure that we, learn from that question. Because you might recall we had 0 people who gave the right answer in class on Friday.
I don't have my phone. What do I do? I know the answer. It's cute.
We're doing well. Now I'm starting to worry.
Wait. I'm trying to get it. We'll just write down a letter.
You said 0 people got it right?
Excuse me?
You said 0 people got it right?
On Friday, yeah.
I do not have my phone. That's not true. I got it right when you were talking about how we got everything wrong.
I can't see it. Okay, so we're slowly coming in. We have Brittany, Hannah. Okay, now we just have Hannah Carmen. Okay, far, far better.
It's almost like we knew the answer because it was told to us last class period. That's a surprise.
Most of the time, even when we discuss the right answer, there are people who come in with the wrong answer again. So over a weekend, there could be more. So who wants to explain? I'm not going to draw a card. Who wants to explain why it's B and not A or C or, of course, D? Hannah.
Well, it can be D because you said predominantly, so it just has to
Okay.
And predominantly, the chemical composition would determine the physical properties because C is like the list of the physical properties, right?
Right. This is the list of the things we measure. And it says the physical properties of a mineral are predominantly related to. And so it's the thing that causes them. And so she said C is the physical properties we measure, not what causes them. And so then it leaves A and B. And why is it not A?
Because B makes more sense.
Because B makes more sense.
I'm sorry, can you say that again? Why is not C?
C is the things that we measure for the physical properties. Right? But it says They're related to what, not what are they. So the question was looking for a cause. And the chemical composition, internal arrangement of the atoms is what gives them their physical properties. The chemical composition and the arrangement of the atoms result from things associated with A. And so, yeah, we went through some logic on how to get that.
So you said the first one is the result of the physical property?
This here, these conditions will lead to these things here that give them their physical properties.
So how can it's not both and?
Because it says predominantly.
Okay.
Okay, next clicker question, one that we didn't see. I don't think we saw this one last time. Silicates are the most common and abundant mineral group because silicon and oxygen are blank.
Well, that's false. Also false.
Okay. Tiffany, and Carmen. Okay. So, wow, we had a very strong agreement here. And those 16 people are right. Silicon and oxygen are two of the most abundant materials in the Earth's crust. I showed you the graph at the beginning of last lecture of the elements in the crust of the Earth. And those are two of the big ones. Now, we didn't talk about why those elements are significant. Remember, we said there's 8 elements that are significant in the entire Earth as far as we know. The reasons for those, as we understand in science, is that the Earth, okay, so this is the scientific view. The scientific view is that there was a big cloud of gas and a shock wave came and caused it to condense and stuff fell toward the center mostly and gave us the sun. Other stuff clumped away from the sun, and close to the sun, it was really hot. Makes sense, right? And if it's really hot to the sun, you can't have things like water or ammonia or something like that. You can't have them stick together. You only have things that have a very high melting temperature that can stick together. And so the Earth, being reasonably close to the sun, could only hold on to things that could stick together at the high temperature. So we have a high abundance of things with high melting temperatures and not much with lower melting temperatures. If you get out past what's called the frost line, that's where it was cool enough for what we call volatiles to stick together. And then clumps could gather a lot more types of atoms, giving us the gas giants out there. So that's believed to be the reason why we have silicon and oxygen as two of our common elements. Okay, so now formation of minerals. I want to try to go quickly because I got 30-odd slides today. So minerals formed by crystallization. I've talked about what it means for something to be a crystal. So can you remind me, as if I forgot, what it means for something to be crystalline in nature or a crystal? Anyone?
Orderly and repeating arrangement.
Okay, crystals have an orderly repeating arrangement of the atoms. So crystals only have a certain arrangement that they will come to. And how does that happen? It usually happens when you have something that either precipitates out of a solution or freezes very slowly. If it freezes quickly, they will just have a hodgepodge relation. And so the situations for making crystals require either you have slowly cooling magma. Magma is the term for molten rock. And in a slide coming up, I'll just have this defined, but I'll say it now, so I'll skip that slide when it comes up. What's the difference in magma and lava? It's simply where you find it. Magma is what we call it when it's underground. When it gets to the surface of the earth and starts flowing, then we call it lava. So they're both molten rock. It's just where you find it is the difference. So if you have slow cooling of melted rock so that it freezes slowly, then you'll have atoms that find the repeatable positions and grow bigger and bigger crystals. Water solutions. Remember on Friday I said you can take salt, put it in water, dissolve it, then let it evaporate, and you can form reasonable sized crystals of salt by doing that. It's called an evaporite if you let it evaporate, but you have a high concentration. As it evaporates, the concentration gets higher, which causes some of the salt to go out of the solution, and if it does it slowly, it'll form crystals. Now, the formation of minerals, we have 4 different things. Yeah, you can read that actually better than I can read it. We have the silicon content, or that's a silicon, but I'm going to go with silica, as you see here, silica content. Things that have a low amount of silica will melt at higher temperatures. So we have higher melting points, lower amounts of silica. And so if we have something that is a slowly cooling rock, the stuff that has a high melting temperature is the stuff that's going to start crystallizing first. And so that's going to start being removed from the fluid. So the actual chemical composition of the magma changes as it cools because you have the minerals taking out what goes into that mineral. Then you have the last things, or the things that have the highest amount of silica or the lowest melting temperature. What is silica again? Okay, my picture, I can't draw 3-dimensional pictures all that well. It's that tetrahedron, is that right? It's got 4 oxygens on it and a silicon at the center. That's silica. And quartz is what we call fused silica. So the more of the mineral or of the stuff that quartz is made of, the lower the melting temperature for the minerals. Here's talking about how it forms in water. So as it becomes chemically saturated, that means it's holding all of the chemical that it can hold. You might remember with our 10% NaCl salt solution that we had in the lab last week, we noticed about halfway through that some of the salt had come out of solution. It was possibly a supersaturated solution, more salt than it can hold. And so the salt came out of solution. So we shook it up to get it back dissolved. Here's something that you may have noticed in rocks. Have you ever seen a piece of granite? So here's a big chunk of rock. And in that rock, you have like a white line that goes through it that's like, you have no idea. That's because you had a fissure or a crack in the rock and water flowed through that crack. And as the water flowed through that crack, just like water going through a pipe in your house, you can have deposits, mineral deposits. Oftentimes it's going to be calcium carbonate that was deposited and eventually fills that crack with whatever kind of mineral was in the water. And so that's what causes those veins, if you will, in rocks, is water going through cracks and depositing more rock. So I've talked about, I think, evaporites. I said if you evaporate water from a saltwater solution, then the concentration of water goes up because the water evaporated, but the salt didn't. In fact, we talked about fractioning of oil. Remember, you take the oil, you heat it up until it's in vapor phase, and then you have the fracturing tower, the stuff that has the highest melting temp or the highest, yeah, melting temperature was right. The highest melting temperature is like tar, oil. You get up to kerosene, gasoline. We had a test question on that even. It's the same idea here that you have when you change the concentration, or excuse me, the saturation level changes. Oh man, I lost my train of thought. It left the station. The same idea that as you have water and salt at a certain temperature, the salt is very unlikely to evaporate, whereas the water is very likely to evaporate. And so you separate things by their melting / evaporation temperature. And so water will evaporate out, leaving us a more concentrated saltwater solution. Because it's more concentrated because it lost the water, then it's saturated, it precipitates the salt, and you continue to grow the crystals. 3 primary types of rock. 3 primary types, let's see. Yeah, 3 types. This has igneous and sedimentary, and I think these are, no, those are not metamorphic there. Yeah, they are. And metamorphic. So 3 fundamental types of rock. The first 2, you might really consider it fundamental, and then the third one, a derivative of them. So igneous rocks are rocks that they formed in fire. They're rocks that were melted and then solidified. So they melted and froze. That's what an igneous rock is. Whereas a sedimentary rock is where you had material that settled. And as it settled, it got compressed and cemented together to make a rock. So sedimentary rock is pre-existing rock that got crushed together or cemented together. And so this is things like sandstone. What are some other? I was going to go look over there. That's cheating. Depending on the size of the crystals, you have different names for them. They're all, my mind is blank. Shale. And there's one in between that we call mudstone, but there's no point in talking about that. Those are examples of sedimentary rock. You also have sedimentary rock with bigger chunks, things like conglomerate, or breccia. Conglomerate has smooth rocks, breccia has rough rocks, but they're bigger rocks that are encapsulated in smaller sediment to make sedimentary rock. So those are types of sedimentary rock. Igneous rocks are things like granite, basalt, obsidian, pumice, andesite, it goes on and on. So they're separated by how they formed, if it was melted or if it was just deposited. Metamorphic is either of those 2 types of rock that has been compressed and or heated to cause it to be squished and misshapen. So metamorphic rock is either of the sedimentary igneous rocks that have been transformed by heat and pressure, and this says chemical fluids as well. So let's look at those a little bit. Here's the difference in magma and lava. I already explained it, so I'll go right over it. Heat. We learned in chemistry section about radioactive decay and radioactive decay releasing energy. And so we had a homework problem that talked about the inside the Earth, the temperature is elevated because of radioactive decay, because radioactive fission of things like uranium. Now, there was a question on the test that dealt with this, and it was one of the ones that I discounted in the grading. But it had for its answers, one of them was the heating in the Earth is because the Earth is made of heavy elements that decay through fission. That was incorrect because the core of the Earth is not primarily those things. Those are trace amounts. So that's why it was incorrect, because it said it's made of those things. If it said it includes trace amounts, then that one would have been correct. Another one said that the fissionable elements were created in the Earth. That's untrue. They were created in the depth of other stars, leaving us with the correct answer on that. Okay, so coming back to this, those radioactive elements are heating material in the Earth. There is a second mechanism for heating material in the Earth. That is gravity from the sun. Gravity from the sun pushes and pulls on the Earth. It causes our tides, high tides and low tides are caused because the moon's gravity primarily, the sun's to a lesser effect, distorts the Earth. And so that distortion, just like if you bend a piece of wire, makes it hot. That's why the moon Io that orbits Jupiter is volcanic, because it's so twisted up and distorted by gravity that it keeps it hot. Ours is primarily radioactive decay, but we have this, an average increase in temperature of 30 degrees Celsius per kilometer you go down in the Earth. So it's getting a lot hotter as you go down. And of course, if it gets hotter, things are more likely to melt. But things don't actually become fully molten until you get way down in the Earth, way above the temperature that rocks would melt on the surface of the Earth. And that's because pressure also relates to melting. If you increase the pressure for most things, like rock, you increase the melting temperature. So as you go down the Earth, both the pressure and the temperature are increasing, and you have that mantle that has temperatures that would melt any rock on the surface of the Earth, but because of the high pressure down there, they're not molten. So the rocks in the lower crust and upper mantle are near the melting temperatures, getting hotter and hotter as you go down, but the pressure is going up and up. So any additional little heat can cause them to melt. And so let's look at, actually, I'm going to skip past this part here because of time and just go to the next question. Even though the temperature or depth is hotter than rock's melting point, the rocks at depth are solid. Why? I'm going to put solid in quotes. Tiffany, Jocelyn, Carmen. Excuse me? Yes, everyone but Tiffany is here. Okay. So we had 1, 4, 3, 9. So why don't you talk to your neighbors about this just to discuss your answers. And then, Raquel, you're going to explain it to everyone after the discussion.
None of this counts for me because I don't have a big top. I've been writing it down.
The
It
one
wouldn't
that's-
turn out, so maybe you should bring it
I think the one that's like that went to-
Yeah.
Worried about the
Yeah. That was my first girl. I don't know. There's a whole episode. I know simple joys in life. Valerie's all the fun.
Okay, let's go ahead and answer a second time, and then, as I said, Raquel is going to be the one explaining. Answer, Casey.
Me?
Yes,
Okay.
please.
I felt.
No. I mean on your clicker.
Oh, I did. I did.
Skyla, Valerie, Vanessa, and Larissa still haven't answered.
I was like 100% positive I answered. Guess it didn't go through.
Sorry.
Oh, we re-answered.
So- Yes, that's right. Okay, so after the second time, the numbers went to 0, 2. That's a 0 and a 2. It's hard to read my writing. 0 and 15. So Raquel, how you feel?
So, I first put down B,
Mm-hmm.
and then after talking about it, I switched my answer to B.
Mm-hmm.
But I still don't know, because I feel like B and C kind of both make sense, but A doesn't make as much sense to me, but they all talk about pressure, which is why I decided to put B.
Okay, you're right. They all build on one another. Because as you go down, you have more material above, and the pressure is the result of the weight of the material above. The pressures increase as you go down. But as pressure increases, the melting temperature increases. It's trying to compact it more, and melting is an expansion process for almost everything. Remember, water was an exception. And so increased pressure increases the melting temperature and prevents melting. And so you would have to have an even higher temperature than it has to counteract that pressure increase. So they all built on each other. So you were right.
Why did you say solid?
Why did I say solid? Because metamorphic rocks are created in these conditions where it's really high temperature and really high pressure. And while they're not flowing, they can be squished a little. And so that's why I put the solid in quotes, because they kind of be squished. Not like sponges. I'm trying to think of a good analogy, and I'm not coming up with any good ones. Kind of like toothpaste in a tube, but harder than that, obviously. Okay, so melting rock occurs over a broad range of temperatures. The things that will freeze at a high temperature tend to be the things that are low in silicate, and so those will freeze first. And so if you have minerals low in silicates and they freeze first, when you get to the end, the last stuff to freeze is going to be high in silicates. So you actually will have a differentiation in the type of minerals depending on when something melted. And so if you have something like a pluton, do I have a picture of Pluton coming up next? Come on, where's picture? I have the word Pluton here. The figure for a Pluton doesn't occur until here. Okay, a batholith is just a really large Pluton. A Pluton is a big pocket of molten rock. So if you have a batholith, a big pocket of molten rock, as it slowly cools, right, because the material around it that's solid, of course, is cooler than that batholith. As it slowly cools, the first things to freeze are going to be the things that have the smaller silicate contents. And so that means the stuff that's forming around the edges as it freezes, that stuff is going to have less silicate content. And the stuff that's at the center, where you're going to have retained heat because the heat's got to get in there, that's going to have an increased amount of silicate content. So if you go through, if this thing eventually freezes and you cut through it, like you guys know I'm from California, we have Yosemite National Park, one of the most beautiful places on earth. And you have things like El Capitan, which is just a huge monolith. That means a single rock. Or you have Half Dome. These are plutonic rocks. They are rocks that were plutons that floated up. And so you have a lot of granite. Granite is what we call the rock that froze very slowly in these plutons. And because it froze very slowly, what does that tell you about the crystal growth?
High.
Has high crystal growth. And so if you look at that granite, you can see there is and you'll see crystals like this big of quartz, and next to it plagioclase, and you'll have different kinds of crystals that you can easily see with your eye because these crystals grew for long periods of time as it very slowly cooled. And if you were to drill through that, you would find different concentrations of the minerals because the ones that have high melting temperatures are going to be generally on the outside. The ones with the lower melting temperatures, more silicate toward the center. Okay, now go all the way back to where we were. So yeah, I already talked about this. Our textbook breaks this up into 3 types of magma. When I taught geology before, it didn't really talk about this difference, but it says basalt is 50% silica, andesite 60%, and granite 70%. I had previously thought that they were all about the same content of silica. I was wrong, apparently. I learned things. So, granitic, that's what we see out there in Yosemite, a lot of granite. The andesite is named because you find a lot of that in the Andes. And then basalt, where do you suppose you find a lot of basalt? The ocean floors. Basalt, we have basalt also, like if you drive through Nevada, you can drive through a lot of basalt as well. But we find a lot of basalt in the ocean floors. These are slightly different concentrations of silica, and you notice 80% of all of our igneous rock is basaltic. Only 10% andesitic and 10% granitic. Just different concentrations of silica in them. Plutonic rocks versus volcanic rocks. These are all igneous. Plutonic, I just talked about what a pluton is. A pillow of molten rock that floats up. It floats up because in the molten form, it's less dense. And so less dense stuff floats up in greater density material. So these tend to float up. And, they solidify very slowly. Have you guys heard of, I can't remember his first name now, Gentry, the guy who talks about finding little halos, polonium halos? Robert Gentry, I believe is his name. You guys are familiar with that? Well, he studies granite. Granite, which, as we understand it, takes millions of years to form. And he finds when you have like a polonium atom, the polonium atom will decay and, well, the radon decays into polonium, actually, is what I should have said. Radon decays into polonium. And the half-life for decay is something like 3 minutes. That means, on average, you'll have half of your decays have occurred in 3 minutes. And if you have granite forming, since it cools over a very, very large amount of time, and the halo is only preserved if it's already solid, then he's finding polonium halos without the radon halo. The halo is actually shock rock. When there's radioactive decay, it releases energy. That energy is absorbed by the rock and makes a little shock wave go through the rock, and you can see the damage done by that shock wave. And so he sees these shock waves for polonium, but not for radon. And since there's only like a 3-minute time scale, he says that means that you had to have the granite solidify in under 3 minutes. And since we can't make granite solidify in under 1 million years, I mean, according to theory, he says there is absolute proof that God made the rock solid granite, and that some of, it had polonium there that decayed, that didn't have the radon. Now, a lot of people argue with that, but he has a standing challenge to anybody. He will give up his creationist beliefs if you can find a way to make granite form in under 3 minutes, which of course no scientist can do. So plutonic rocks, they cool very slowly, should have large crystals. Volcanic rocks, the magma came to the surface, still melted, freezes at the surface. Well, the time it takes to freeze once that magma gets to the surface is going to be measured in days, right? Sometimes hours or minutes. So the time for the freezing of volcanic rock when it came up to the surface is much shorter than the time for freezing of the plutonic rock. As a result, you don't have the time for big crystals to form. So the volcanic rock tends to form rocks where you can't see the crystals. They might have little tiny crystals. So basalt has tiny crystals in it. Obsidian has no crystals. Why does obsidian have no crystals? Because it freezes so quickly you don't have time for them to form. You don't have time for the atoms to find, oh, this is a lower energy configuration. And so those are two distinct separations in the igneous rocks, ones that cooled slowly and ones that cooled quickly. Now, as to volcanoes, where's the nearest volcano from us? Where? Washington. Okay, now if I said the nearest active volcano, I would take that as the correct answer. And then you get into the technicality of what makes a volcano active or inactive. And it's how long it's been since it's erupted. And there are some schools of thought that there's really no such thing as an inactive volcano. The closest volcano, and the one that we worry about the most, is Yellowstone. Right? What is Yellowstone? It has a really big magma chamber underneath. If you've gone there, you've seen that there are pools of extremely hot water. What was it, a year or two ago? A guy fell in. Yeah. You don't survive those things, right? Why is it really hot? It's because of that magma chamber down below. And that magma chamber has come up to the surface and erupted a number of times in the past. So if you ever find your way up to Ash Falls, it's a place, it's a place where a farmer discovered these fossilized animals buried on his property. And the University of Nebraska has done a lot of excavation to dig out all these different animals that were buried in the volcanic ash in the rock, blew up into the air, solidified, came down as a powder, and then was compressed and lithified, became a rock that we call volcanic ash. And so you have all these things there. Very devastating. If it erupts again in our lifetimes, it may be inhospitable to life here in Lincoln. So it really is a concern if it actually erupts. So every now and then you'll read people, posting either real news or fake news. Fake news. All of the bison in Yellowstone were running away. Must be about to erupt. You guys see that article? Yeah, it's not real. But they're making measurements of that magma chamber, and it appears to be growing and filling and scaring people. Question, Brandon.
What caused them exactly to erupt?
What causes them to erupt is, as I understand it, basically you build up enough magma pressure in that molten magma to make it punch a hole. Now, of the volcano types, we have cinder cones, which are like that, right? The cinder cone is the idea of you have something that's erupting up, stuff falls down on the sides, creating the cone. Or you have shield volcanoes, and you can see here the shape of the shield volcano is somewhat like the shape of a shield. That's where it gets its name. Shield volcanoes are formed when you have a magma that is kind of runny, it can flow, and so it just comes and it flows out over the surface rather than erupting in a big energetic eruption. These shield volcanoes are what we see in Hawaii. The entire Hawaiian island chain is the result of, believe it or not, one volcano. And I'll talk about that in a few moments here. Cinder cones are where you see the big energetic eruptions. Composites are actually basically cinder cones where you have had stuff break down and like slide down the slope and make it flatten out. So the composite is tightly aligned with the cinder cone. So here's how a volcano forms. You have a magma chamber down here. You have some kind of pathway that it forms up to the surface. You see here, what kind of shape does this volcano have? It's got to be something like composite. It looks like it's a shield volcano, but its shape looks so much like a cinder cone that it's hard to really tell. The fact that you have lava flowing here means that it really should be classified as a shield volcano, because if you have lava flowing rather than a big pyroclastic eruption, then it's a shield volcano. This here, that's rock that you see here, you had something that came up here and formed a layer like this that has reached the surface and had erosion go away from it, so you see that rock. This is, why did it do nothing? There we go. Oh, wait, this isn't I thought this was a clicker question. I was like, I don't have any more clicker questions. What did I do wrong? My brain isn't malfunctioning again. Sedimentary rocks. How do we make sedimentary rocks? There's a 4-step process. We have misconceptions of what these terms mean, because most people think erosion is what weathering is. You know that when you go hiking out there at, let's say, Holmes Lake, you should not walk down the little dirt path from the dam, right?
Did not know that.
No, you shouldn't.
Wait, what?
That's why periodically they will put tape there to try to keep people from walking down those. Okay, why though? Why is because that will cause weathering. What is weathering? That's breaking the material away. Now here this is talking about rock, so it says breaking rock. Actually, I put in breaking rock. But weathering is breaking material away. So when you walk down there, you have this soil that's held together. You're going to cause some sliding, some breaking of that soil. And then once that soil has been broken, then you can have the erosion process, which is transporting that broken material. So when you go off the path, and you go hiking in Yosemite once again, if you go off the path, then you're going to cause weathering of rock that you walk on. And then things like water, rain, or even wind will cause erosion. The stuff that you broke away will be removed from that place. And so that's going to degrade the rock. So, that's why we have rules, stay on the path. As a child, I didn't understand. I was always running off the path. But then when I started studying geology, I started doing the right thing. So, erosion, breaking the material, or weathering, breaking the material away, erosion, transporting it, and then we have sedimentation. Something transported and eventually stops moving. That's where you have the deposition, where it's dropped out, and finally sedimentation. Now, where do you suppose you have most of your sedimentary rock made? Okay, bottom of, let's just say water. Okay, why? Because a lot of the erosion process is water driven. So you have water that flows over a rock, if it's been weathered, then the water will pick up the weathered material and transport it. It goes into a stream. As it goes down the stream, it continues to move until you get to the water slowing down. So if the water comes into a lake or the ocean, the water speed slows down. It starts dropping out the stuff it was carrying. So if you look at, for instance, out by New Orleans, you have a big delta. I think it's New Orleans, isn't it? You have a big delta, and that delta is where material that has been eroded and come down, it's got to be Mississippi, then meets the ocean, slows down, and gets dropped out and leaves just all of this sediment on the bottom of the ocean there where it slowed down. And then finally, you have rock formation, a process we call lithification. You compact it, you push the water out, introduce maybe some chemicals like calcium carbonate that will hold it together, and you make your sedimentary rock. So looking at each step individually, you can have mechanical weathering. That's what you and I will cause as we walk on rock. Chemical weathering is like if you have acid rain, that's going to cause a breakdown of calcite rock. So that would be an example of chemical weathering. Frost wedging. This is a problem out here in Lincoln, especially for our sidewalks. Because when water freezes, it expands. And so you have a crack in the sidewalk. You get some water in there, it gets cold and it freezes and it expands and it pops that crack out a little bit. It also causes really interesting things you'll notice, like slumping of hills. You have something like you put your fence posts in vertically on a slope, and over time they start tilting. And the reason is, as you go through a freeze-thaw cycle, when you freeze the water, you actually have the soil expand a little. And so if it's on a slope, it expands up and the direction away from the slope. And then when it thaws, it drops straight down due to gravity. And so the topsoil slowly migrates downhill when you go through freeze-thaw cycles. And so that makes your fence post or your tombstones start to tip over time because the topsoil is moving downhill. So that is another problem here that occurs related to the frost wedging. Thermal expansion is obviously closely related to frost wedging, but it's now talking about anything, not just water. Biological activity is clear. That's where you and I come in. So erosion, just the motion. There's nothing really talked about erosion. Deposition is dropping stuff out. If you have fast-moving water, it can hold bigger pieces. Slow-moving water, it can't hold as big of pieces. So you will have, if water is going quickly along, it'll carry a lot of material. If it slows quickly, then you'll drop all of that and you'll have all kinds of different sizes. If it slows slowly, if the speed slows down just little by little, then you'll be dropping out the bigger pieces. And so you end up with this idea of sorting. This is called well sorted because all of this is small grains. That's not how I spell grain. This one here is poorly sorted because you can see it has some much bigger grains compared to other sizes. So sorting is something that tells you about speed of water if it's in a alluvial. Let's not worry about that word. Lithification, the actual process of making a rock, occurs when you have, well, I've already said this, compaction from pressure, and then cementation, some kind of chemical that makes it so that it gets hard. So when you compact it, you release pore water, it takes out the water, makes it stick together. I'm so out of time here. Here's the different types of sedimentary rock. I listed shale, sandstone, and conglomerate. And then I listed breccia as well. So you can see here the definitions of what makes shale, what makes sandstone, what makes conglomerate. And this here is a coquina. I have to mention it because what it is broken up shells. Okay, we're out of time. I'll see you on Wednesday.